Now I would like to try an example of calculating electric fields. And the example I'm going to use is actually going to be based very closely on our first example. So this way we can make some comparisons. So in this new example, this is the second example then for the course, example number 2. In this example, I'm going to have a x-axis once again, and I will have my two charges again, Q and Q, each situated at equal distances but in opposite directions from the origin. I will again consider a point on the z-axis at a distance z up above that axis. But the main difference from our previous example is that I am not going to place an actual charge at that location. I'm going to leave that location empty. That's why I'm writing it or denoting it by an open circle. And what I want to ask instead is, what is the value of the electric field at this particular location? Now, as a preamble to this, and particularly since we've just been thinking about directions of electric fields, I think it would be useful just to try to determine the direction. So let's make a couple of guesses before we really delve into the problem. It's always good, actually, to do this. It's a good way of checking your results at the end. You have to make your guesses first, though. Otherwise, you'd be biased by what you actually calculate. So we're going to make a guess here for the direction of the electric field. And remember what our procedure is. What I'm going to do is I'm going to imagine, and for the sake of this problem, I'm imagining these two charges down here are positive, right? So supposing these were positive, what would the direction of the electric field be at the point up here? Well, the way we determine this is we put a small positive test charge at that location, and we ask what way would the force be on that positive test charge, and then that will give me the direction of the electric field at that point. Well, if I were to put a positive charge up here, I think we can see what the direction of the force is going to be. There will be repulsion from this charge over here, generating a force that's up and to the right. There'll be repulsion from this charge here, generating a force that's up and to the left. The left and rightward components will cancel, and the electric field will be straight up. So the first guess I'm going to make is that the electric field at location Z is in the upward direction. Now there's a second guess that I can make here. And this is a little bit more of a sophisticated way of doing the guess, but I want to leverage what I already know from the previous problem. In the previous problem, I had exactly the same situation, except I had a charge actually sitting at this point, feeling an actual force from that electric field. And we had worked out what the value of that force is. And I'd like to relate that value back to this electric field, which I'm trying to calculate. And you can see here what the relationship is going to be, right? The electric field at that location, via this formula, I can solve for it. It's just going to be the force on my charge capital Q divided by capital Q, the charge. That would lead me to the electric field. So my job will be then to take this formula for the force and to divide it by capital Q, which will cancel this one factor of cap Q in the numerator, and then what's left will be my guess for the electric field. So if I write that out in a little more detail, what I'm using is a general principle that the electric field at a given point is going to be equal to the force on a charge sitting at that point divided by the charge. And a little comment I'd like to make for you here that will be useful to keep in mind is that this tells you what units the electric field should have. The electric field always comes in units, notice, of force, measured in newtons, divided by charge, measured in coulombs. So the units on electric field should have units of newtons per coulomb, our natural units for our electric field. We'll learn some other units for it later, but right now let's stick to newtons per coulomb. And in our particular case, when I divide by capital Q, as I said, I simply copy this, neglecting the capital Q in the numerator. So my guess is I will actually get Coulomb's constant times the two charges, and then there will be the factor of Z. The direction will be upwards, K hat, in my guess. Notice that that is completely consistent with my previous intuitive guess for the direction of the electric field as being straight up. And then I have my favorite denominator, of course, which is r squared plus z squared to the power 3 halves.